right, well, welcome to week 7. And here is what we're going to talk about is rotating imbalance from sections 3.2, 3.3. Here's some suggested problems. I actually found several of them, 2, 3 of them, to be on the difficult side and not really as related to what was in this section right in there. So I have some example problems that I think are more appropriate for what we're trying to do. I would favor those over these. All right, so here is some of the big picture. The book does a quick derivation, not very long, but you could just take a look at this yourself and see that right there, if you did a free body diagram of a forces right here, so that's going to be the force. Let me put my laptop back into writing mode. Here we go. Instead of trying to write on the screen while it's vertical. And you took an IBD. Actually, let's just get rid of that thing. Let's just start over. And so if you have an FBD of this mass right here, this eccentric mass, little tiny mass, he's got a distance E, and he's rotating around right there. So that right there is going to be your omega F, and of course it's next to T, so I'll write those both together right there. So that's going to be this guy. Usually we put an F in here, right here as well. So if we have like a normal and tangential coordinate system right here, the force that we're going to be imparting on here is going to come down that right there. So it's going to be like, that's going to be this transmitted force. And then for the ball, we'll pretend that it's moving at a constant velocity, right? So it doesn't have an angular acceleration, only an angular velocity. And therefore, it's going to have an MAN, right? It's pretty simple right there. F is going to be equal to F, let's call it Fn as well. So the sum of the forces in the n direction equals mass times acceleration in the n direction. And so Fn, in this case, is going to be this little mass times the normal acceleration. Now remember that the normal acceleration can be written out as v squared over rho. If we're going around a curve, it's the same thing as r theta dot squared, right? So if you were to say, well, I can't see how those two things are the same, recognize that v is also equal to r theta dot. So if we put that back into here, we end up seeing that we get like r squared theta dot squared over rho, which is actually r, right? Well, I didn't mean to cancel it all the way around. So just the square cancels out right there. And so you can see that these two are equal to each other, which is the same thing as r omega squared. So we go r, and we want to use E for the eccentricity here. So we go E and then omega squared. So here's a force. They did a little bit of manipulation onto this previously in one of the versions of this. What we had seen is we took an X is equal to F, and we'll go with O, whatever you want to call it, divided by K, and then this below here became like well, we worked out some additional versions of this equation. But in this case, what they decided is to keep the K down in here and move the mass there. And then over here is another version, yet another version, where we have now manipulated. We took the big mass out and the little mass out and put it over on the left-hand side. Here's the eccentricity. This is the X is the amplitude. And then quite often what we've been doing is we've been calling that R. So you'll see this one looks fairly different, just really just the R squared being on top. But that's one of the reasons why is because we took the mass out and we also took a K out of this thing. So there's not that much of a difference, but it does result in a slight difference when we come to this transmissibility, right? So this is one where this is the base vibration due to an unbalance. And I've also included, I've also included a phase diagram up in here. So we want to take a closer look at that. I'm going to do that in a whole nother section I've decided to call week 7.5. So we will do that later. Anything else I wanted to say? No, we're just going to jump into some uh, problems. Let's see. How do I get out of this thing? I think I had to hit end somehow. I don't have my mouse with me. I got mad. Let's see. End show. Yeah, describe. No, I gotta go down to here. Yeah. No, not you. Oh, that guy. There you go.